So I will be talking today about operation challenges in integrated mobility systems. Sorry for the Zoom part also. And so it's a big project going on with many actors from many different universities and fields. So I won't present everyone. I'm pretty sure you know some of them, but I will present the different fields involved in this project. So there is many professors and students from Polytechnique Montréal working in transportation and optimization, and also telecommunication. There is also a professor from University of Montreal, which is a law professor. From Laval, there is someone in philosophy and in optimization too. There is also someone from l'ENAP. I don't know if you know, ENAP is the École Nationale of Public Administration. And so someone of public administration, and someone from cybersecurity from UQAM. And the last one is people from RTC, which is the Réseau de Transport de la Capitale, which is the equivalent of STM or RTM in Quebec City. So let's talk perhaps first about integrated mobility system, or also known, I prefer use integrated mobility system because for me it's a little larger than MaaS, but it's nearly the same. So MaaS stands for mobility as a service for people that do not know. And the main idea is to provide many services through a unique platform. So it means that you have one app, and from this app you can book a multimodal trip that will be, for example, giving you a ride-hailing service to the subway, and then you take the subway, and then when you go out of the subway, you have a bike and you finish your trip with a bike. That would be ideal. There is not this type of platforms in many cities. Some of them, most of them are in Europe and perhaps East Asia. And there are many services and many different type of system that exist. So it really goes from the traditional, I would say, public transit operator modes, but you can really add whatever you want that can be plugged into those systems. So yeah, bike, but you can also have scooter sharing. You could have Uber could definitely be plugged into that, or more traditional rental car services like Hertz or Budget could be plugged into it. So the idea is really to give you a unique platform where you can order all the different mobility services that you need. And the idea also is that come with it is you have not a unique fare, but I would say a big set of fares that you can choose from it. That, for example, monthly plan, where you can use as much as you like buses, subway, and more traditional public transit system. But at the same time, you will perhaps have some minutes of bike systems, or to rent a car, you can have days or things like that, that comes with your monthly plan. And so it gives you flexibility. The main idea of that is at the end to push people to not use their car, or even more to not own a car. So that's the end, one of the biggest end goal that you have with all those systems. So let's see the main advantages. So as I say, it's sustainability, and this goes by the removing or the reduction of solo cars. So even if people are still traveling with car, you can hope that they will carpool, that they will perhaps drive a smaller distance to go to a hub to grab a bus instead of going directly downtown to the city. And so you try to reduce that, and it leads for sure to reduction of congestions, reduction of parking spaces within downtown, and those spaces could be reused to do some other things. Could reduce also urban sprawl. With remote work, I'm not sure it's not as true as before, as people perhaps as they don't need to go as often in the city, can live more, I would say, far from the city. But the idea is if you have a good mobility system, perhaps people would like to live where you can have access to these mobility systems. Improve user experience. So for sure, you have only one unique platform here. If you want to do this kind of things, you need to have a plan with Communauto. You need to, if you want to rent a car with Hertz, you need to go directly there. If you want to, perhaps Big C and Opus, it's a little easier now, but still, you don't have a unique platform where you can order everything. I think RTM in Montreal is planning to try to have this platform, but perhaps it will come out in 3 years, something like that. It's not for the moment. And we'll say 3 years now, but perhaps it's going to be 5. And so you have multiple services. So perhaps you won't be, or you even not thought about using some of them, but because they are easy, you can have an easy access. Perhaps also they can be part of the plan. So most of the time in this system, you will have a big bundle. So perhaps there are services that you may want to use, but at the beginning, some other services that are part of the bundle that you didn't think you would be using, but as you have a free access to it, finally, perhaps you start to use them even more and more. And so you can increase adoptions of the services thanks to that. And the last part is most of the time you have a comprehensive and flexible price. So that's many advantages, but there is also some potential drawbacks. I think the main one is the competition that you have among operators. So you have many operators that they propose different mode of transportation, but in terms of origin and destination, they bring you from the same place to the same place. So as a user, you can choose among them. And sometimes, especially at the beginning, for example, of Uber, if you're looking in city like San Francisco or Los Angeles, what happened is people, so you had a big increase of ridership, for example, for these ride-hailing services. But the problem is the people that were using those services were not people that were using their car before and decided to stop use their car and use those services. That was the advertisement that was made, for example, by Uber for years. But when you were looking at that number, it was the opposite. What that was happening, it was people that were used to take the bus, that stopped taking the bus and use Uber instead. And so you had an increase in congestion, increase of, and a destruction of those services. Because if the ridership in the bus decrease, the frequency of these buses will also decrease and the quality of service decrease. And you have perhaps even more people that will start using Uber and so on. So you have the destruction of the services in this city because of the competition that you have between operators. The other, I think, big issue for me is the huge fog that you have around the large amount of data that are collected, especially by private operator and the usage they're making of it. So you have, I won't say no idea because so who's reading really the big policy that you have at the beginning when you agree to use as a service? I'm pretty sure no one. So perhaps you will try to control a little the, I would say, permission that you give to the app in terms of locations or things like that. Through time, I would say that the most manufacturers of phones are trying to give you more and more finer control on when you give the permission for the location. But at the beginning, it was all or nothing. So you were giving all and they were taking plenty of data. That's perhaps less true now, but still they are using a lot of data and you give them the permission for it. And the question then you can also ask is, what do they do with this data? Honestly, I have no idea. And it's very difficult to know exactly what they will be doing with it. So there is a huge fog around it. And the last thing also we can think of potential drawback is the equity of access. People that are using Uber, for example, if we're just not citing one, you are rich. For people, I would say, people that are coming from less favorable region won't be able to pay for Uber every day, and they need public transit to do that. And so you don't want to destroy public transit because it will increase inequality between people. So for the same reason, competition among those operators can have many drawbacks. And so if you want to build an efficient integrating mobility systems, that implies that you need a good collaboration among the operators. And that at many, many levels. So if you want to serve the whole area, you have to decide a little, how do you share the area among all these competitors to be sure there is not one competitor that is destroying other operators. You need also to decide how to share the revenue. So as I said, on the system, very often you will have a huge bundle where you can use different services. But how do you at the end share the revenue of this that you have with this plan among all the operators based on usage and so on? So you need to find some common rules where everybody agree on it. And also sharing the data. I think that's the biggest issue. I would say that public operators, normally they share the data, at least they share the data between operators. They would share the data with other public organizations. They may be a little more reluctant to share the data with private operators because they know that private operators do not share the data back. And so if you want to be able to build efficient system, you need some data, you need to know what is happening in your system. And so you need different operators to share the data they are collected. And ideally, then you also want to synchronize the services. So it means either on the planification level, ensuring that two operators that are working on, I would say, connected area, ensure that their services connect well together. So that's on the planification part, but you can also try to do that in real time. And you can pretty sure think to many other issues and things that need to be settled. Then to do all that, what you need to do is to set some public, ideally, governance rules. And that comes also with many challenges. So if you have a unique platform, is it privately owned? Is it publicly owned? Do you have a public, I would say, administrator, or is it just all the operator that they are the administrator? What are the rules that say how you use the platform? What do you share? How do you share revenue and so on? So that's, I would say, one of the toughest parts from, perhaps not first from the optimization part of view, but to see those systems, that's really, really difficult. And so if you want, especially public, but in general, you want to increase equity, you want to increase privacy, you want to increase ethics on how everything is done on those platforms, how the data is collected, which data is collected, how it's used, and so on. So I will talk today about different challenges, some that are more, I would say, OR-oriented, but most of them are OR-oriented. And I will spend more time, I think, on the last three. The first one is just to give some broad ideas on what can be done and things that can be done in terms of research. So first, revenue management. So the idea is, how do you price the services? How do you price the bundle that you offer? How do you price the plan that you offer? And how do you share also the revenue among operators and so on? And so the idea is, depending on the plan that you're doing, the pricing that you are doing, you will have a huge impact on the behaviors of the riders of your system. So you need to play with these things, and I think it's what mainly most of operators are doing now. It's how to find a fair price that helps you to run your system, but at the same time, ensure that you have a decent amount of people using the system. So for example, you can see that RTM, everybody know what is RTM? Yeah, no, it's the big administration that manage all the transit system in the Montreal larger area. So it's STM is one of the operator of this big organization, but you have STL also, which is the transit agency of Laval. You have EXO that operate all the trains and different services around. You have also, I forgot, RTL, the one of Longueuil for the South Bank, and so on. So they are the one in charge of making the fares, sharing the revenue among the different operators of the greater Montreal region. And so they just changed the fare, I think perhaps 1 or 2 years ago. And for sure, this modification of the fares has a huge impact on how people are using it. So if you were living in Montreal, I don't think it's a big change, but for people that were living outside of the island, I'm pretty sure it changed the behavior of some of them, because perhaps the price increased, and so they use their car. If you live in zone 3, perhaps you would use your car to go to a zone 2 big parking lot, and then take the subway, for example, instead of paying the full price from here. So that's different. The other thing, for example, that you can see as incentive that the RTM has done here, it's really recently because I think it's a few days ago. There is a big renovation work on the Tunnel La Fontaine. And so that has a huge impact on all the congestion that you have from the south of Montreal to the island. And so what they have done, they have released a new app to push people to carpool together to reduce the number of cars on the bridges and try to reduce congestion. So the idea, if you carpool, if you are someone that are picked up by a driver, you have to pay a certain fare, I think, per kilometer. And if you are the driver, you receive money in exchange for the people that you take with you by kilometers. So what people are paying to get inside the car represent less than what the driver gets. And the difference is covered by the RTM. So the idea is really to push people to carpool to try to reduce the number of cars and the congestions on all those axes. So definitely you have a huge impact on the behavior of the rider depending on the fares and the way you set the prices. And also you can think, and then it start to be a little more complex, but you can also set prices dynamically. It's definitely, for example, what Uber is doing when you talk about a surge and you have the price that skyrocket. And it's definitely because you are in a big peak and you don't have any drivers, so it's increase the prices. So you can think also from more public point of view, trying to have some prices that push you to adjust when you go to work to try to travel off peak instead of during in peak. So let's talk now about data collection and usage. So as already told, private operators tend to collect as much data as they can. And so you want to control that. You want to, because I would say many users are paying more and more attention to their privacy, to the data that are collecting on them. And also policymakers are starting to pay attention on these kind of things and trying to control the amount of data that are collected by companies and operators. And the biggest issue is private one, as I said, they're very reluctant to share it. However, if you want to have a well-designed, efficient, and calibrated transit system, you need data. So especially what you need is good quality of demand prediction, so which we call OD matrices, origin destination matrices. Ideally, what you want is even more than that. So you want the origin and destination, but you would like perhaps also the mode of transportation used by the person. You want the timestamps that coming with those matrices. You are not just interested on how many people started from one origin to go to one direction within a day, but you would like to have a finer granularity in terms of timestamps. So perhaps how many people travel between 8 and 9 AM or things like that. And so to be able to build those accurate matrices, you need a lot of data. And for the moment, we don't have those ones. So even when you take the bus or when you take the subway, you have your OPUS card, so we know where you get in the subway, but we don't know where you alight from the subway or the bus. So we can try to guess when you alight from the bus, we don't know when exactly, and we don't know where exactly. So even already building these OD matrices are much more difficult. But when you are taking on-demand transportation, you use an app, you know exactly where you have been picked up and you know exactly where you have been dropped off. So here we have very accurate data, but we are not able normally to get access to that data because it's privately owned. And so how can we push operators to share that data together and at least share some of it to be able, then from an optimization point of view, being able to design correctly the network of those systems. And on the opposite, what also we want to do is try to control and limit the amount of data collected by those applications and those operators. So let's talk, for example, of Flexibus. So it's a new on-demand ride-sharing services that has been working at the RTC. So in Quebec, it's from perhaps a year now. So it's the outskirts of the city, and you can use it to go just within some region. And the idea here is to feed some bus line that goes downtown or to help people to move in those areas that are not well served. So here you use an application because it's dynamic ride sharing. And so when you do a request, you have exactly where the request has been made and where you want to go. So you have very accurate data about that. However, they don't know how to share it because it's very sensitive data and they don't want to share it with anyone because they don't know what you will be able to do with those data. So even if you have now access to this data, the question that you may ask is how to use it, because you cannot share this data with anyone because you give a lot of information about what you do, where you work, when do you do your shopping, for example, to which bar are you going, and perhaps even more, you can try to guess or infer whose people are you meeting. If there are different people that are using the same system and you can see some pattern, you can infer a lot about the life of people just about with GPS traces. So you need to protect the way people use this data. For example, if you took a look at the Opus card in Montreal, or I think it's even used also in Quebec, they try to forbid tracking user across operators. So what does it mean? It means if you use your Opus card in STM, you have a one ID that comes with your ID card, Opus card, and so you can track the person through the months and to know where the person tapped his card. But as soon as you use the same card, but in STL, for example, at Laval, the ID number that come with it is different. So you cannot know that it's the same person that board the bus in Laval and take the subway then in Montreal, because there is no way to do the link between both. And as you can imagine, if you are looking at the subway, there is too many people that coming at the same time in the subway to really, perhaps with some optimization, you can try to realign a little those numbers, but I'm pretty sure there will be a big margin of error on it. So that's the way they try to impede people to track too much data about the users. But at the same time, it means that those data doesn't exist anywhere. And you are losing a lot of information also at that part. So perhaps there is a balance to find between both. So really the question here you can try to think, and also there's many research to do on that point, is how to try to track these people or use this, I would say, really accurate trace about origin and destination of those people while keeping their privacy. And it's even more important that there is a new law in Quebec. So it's the law 25, that there is several, I would say, plans within this law. So one of the big things was, I don't know if you heard about it, is the Commission d'accès à l'information du Québec, la CAI in French. So it's a way, if you need some public data, you can ask to this commission, and normally by law, they have to give you the data. But one thing that is really strong with this law, and it would start in September of this year, is that companies now that they have two choices. So for example, the data that we're talking here about origin and destination of GPS point is very sensitive data. So they have two choices. Either they destroy the data because they won't have the right anymore to keep it. Either they need to anonymize the data. But the important point here is irreversibility. So it means that the way it has been done, there is no way to find which person was behind this data. And that's very tough to do, as we would see. And so the question is, how can we still be able to keep this very useful data and be able to use it? So let's take, for example, I want to walk from the campus mill to here at Agenstadt. That's my GPS trace of the path that I have done. So let's say I want to anonymize this trace. I just remove my name. So I'm giving you the trace with the timestamp. That's the trace. That's not enough for anonymization, because you can definitely have access to external database that give you some other information about me and many people in the city. So where do I work? Where do I live? Perhaps I've been to public event or I've been a presenter in some public events. So I know I was at this place at this time. And so you will be able to re-identify and find that this trace was mine, even if you just remove the name. So for anonymization, and especially if you want to be irreversible, it's totally not enough. There's been many research about those traces, and they found that most of the traces with only 4 points, you can re-identify the trace with, for sure, some external knowledge about the people. But we're talking here about public knowledge that you can find on the cloud, on the internet. So that's not enough at all. And so anonymization is a very, very tough problem. And the main reason is you have two things. You have on one side privacy. So you want to be sure you are not able to find back the owner of the trace. So if I want to do that, that's pretty easy. I'm destroying totally the trace. For example, I was doing this trace this morning. I put the evening as a timestamp. Instead of going from the campus mail to I just type, let's say I'm going from this point to Saint Justine. So it's a different trace, different timestamp. And okay, there is no way we would put this trace with me. But at the same time, how useful is the new trace that I have in my data set? Timestamp has changed and the origin destination has changed. So you need to find a balance between both. To be private, you will need to destroy a little the trace. But at the same time, if you want to keep some usability, you need to destroy it, but not too much. And so you have to really find a balance between both. And I think from our side, from operation research, what we need to think about is what type of data do we need? For example, if you're doing some network design, do we really need that I'm leaving from campus mill, or do we need just to set a kind of large area around campus mill and saying just I'm leaving from this area? So yes, we are destroying a little the data, but perhaps from the optimization point of view after that, that's not an issue at all. So you have to think how to use the data after and what you want to do with it when you do this kind of anonymization. And the problem is that perhaps for other application, we destroy it. If we destroy it this way, it will be a huge issue. And as it's done irreversibly, you cannot do anything after that because you will have destroyed the original trace. So to continue on that, if you have many users that are doing the same trip, it's really easy to anonymize because let's say you have 20 users that are doing the same trip or similar trips. And so you can average them and you can try to anonymize, and knowing which one is among this one, 20 users or 100 users, it's very difficult. But the issue is when you have very few users doing the same trip. Here, for example, if you have only one user that is doing this trip, you can definitely identify the person. And the problem is that these few users generally are the most expensive to cover for a transit system. So if you lose this information, you lose a lot because then serving those one gonna be very expensive. So you want to be accurate on those users. So for example, there are some techniques where you can perturbate the numbers of users that have done this trip. So if you have 20, if you say, oh, it's 21 or 19, you don't care. But if you have only one and you say, oh, it's 0 or 2, that's a whole new universe. 0, you have nobody to serve, or in more than 0, you have some people to serve. And so those techniques were just perturbate, for example, the counts, which is known as differential privacy for those that knows these techniques. It doesn't work, for example, for this type of things where you don't have a lot of data, but you still need it from an optimization point of view. So I think there is really many opportunities here for research project. For example, we can think of another way. You want to train a model to predict ODs. Are you sure that the model that you have trained, you won't be able to re-identify the traces that you use to train the model? That's open questions. I'm pretty sure there are people working on this type of problem, perhaps with other things that GPS traces. So you have trained a machine learning or deep learning model. Are you able to identify the data that you use to train the model? But definitely here it will cause issue. And especially as we saw, there is a law that tells you now that it must be irreversible. So it means that you cannot be able to find some original data. So if you're able to do this reverse engineering here, you have an issue with the law now. Let's continue on the user privacy. there is also another way you can try to preserve some of the privacy of the users is simply by not sending the data. So you would try to keep as much data as possible on the phones of the users. And so that's really good in terms of privacy, but in terms of optimization and systems, it makes everything way more complex because you comes into the, I would say, the world of edge computing. So it means that you offload some of the computation that you are doing normally or classically on the central server. Now you will be doing part of it directly on the phone of the user to keep the data on the phone of the user and perhaps just send the results to the cloud servers. And so the question that you may ask now is, in terms of optimization, how can you build those systems where you have very large distributed system, so multi-agent systems with some of the computation that is done on the phones of the user and some of it that perhaps will be done on some servers. So let's talk now about more, I would say, yeah.
I have a question before going to the organization. How is the difference like the privacy between like this type of data you could collect, let's say on a cell phone, compared to like ODD like sondage or
Paul?
Yes, where he asks you like specific questions.
But first, your answer is based on the, if you want it, it's voluntary. So you're agreed to release this information. Most of the time on polls, there is they really tell you exactly how this data would be used, which is not the case at all with those applications. And also a poll is just about generic information on how your habits in terms of mobility. Here, GPS trace, you know exactly where the people have been, where they are going. So it's much more invasive in terms of privacy. So let's talk now on, if you want, with all this issue in mind, how can you try, for example, to assign passengers to the different modes of transportation that are available on the system. So traditionally, it's what everybody is doing. When you want to go from a point A to a point B, you, for example, I don't know, open Google Maps or Transit, and you look what are the different options that are available to you. So by the way, when you do that, you give plenty of data to Google or to Transit, because you tell them that you want to go from this point to this point, and it's already very valuable data for those platforms. And you give them that for free. And so then you have plenty of mode of transportation and you choose whatever you want to do. The problem here, when you try to model that, if you ask to someone if you prefer to ride a packed bus or be picked up by a taxi, you may guess what they would choose, but it's pretty easy. So it means that you need to take other constraint of the system into account. For example, the first one would just be the price. I'm pretty sure it's way cheaper to travel in this bus than to take a taxi. So that's a way to push people to travel in the bus instead of taking a taxi for all the rides and the trips that needs to do. But there is also an issue in terms of capacity. You see here, it's going to be difficult to put more people on this bus. So you have also to manage the number of people that are using different modes in terms of capacity, and design also your system so you have the right capacity for the mode of transportation. So let's take, for example, here, another example. You are in Quebec. You are living from your home and you want to go to your work downtown Quebec. What you do, you use this parking lot where the buses are going and leaving, and they will bring you to downtown Quebec. This one, they are called Parcobus in RTC. So it's a huge parking lot. And so now with their demand, they have their dynamic shuttles, so Flexibus, that can bring you from your home to their place, to this parking lot. You can use your own car, and you can think also, for example, you may be able to carpool. And so depending on the mode of transportation that you are using, in terms of sustainability, first, it's not the same. But then you can also have many capacity issues. For example, if everybody wants to use this dynamic on-demand shuttle, you won't have enough shuttle for everyone. You want to build efficient routes. So you want to select people that are not too far from each other. And so perhaps if there is someone that lives really remotely from the other, you would prefer from a system point of view that this person use his car instead of trying to be picked up by a shuttle, because it's going to be very expensive for the system to send a shuttle to that place. Same if you have two people that live remotely, perhaps you may want to try to push them to carpool together to go to that place. And even more, so for the moment, you don't have, for example, at Quebec, any capacity issue on the parking lot. But in the future, you can imagine that you don't have enough parking space anymore also on the parking lot. So if everybody is going for their car, they won't be able to find a space to park their car once they arrive to the parking. And so you have this problem where the rider will try to still perhaps to choose what they can to do. So you will offer them proposition where of the different mode of transportation that they can do. And at the same time, you try to control the number of cars that are going to the parking. So that's a tough optimization problem because you have it's a distributed optimization problem. The platform that are giving the different proposition of modes are not the operator also. So it doesn't mean that what you think as a platform was I would say efficient will really be efficient in practice, because the operator could decide to serve or operate differently. And so you need to find a good way to, I would say, assign passengers to the different mode of transportation. So the main goal here when you are doing this kind of thing is you want to maximize the overall throughput of the system. And so there's some challenges. I think this one is the main one, as I said, is each service is controlled by the operator and not the big, for example, if Google Maps offer you different option, it's just offer option, the application just offer option. It doesn't tell you how the operator would serve you, how they will operate the vehicles, and how things are really done on an operation point of view. So it's just an approximation. And if you are talking about dynamic shuttle, perhaps you will get a waiting time, but it doesn't mean it's going to be the real waiting time. So when you do your decision to take it, they say you have an advertisement of 5 minutes of waiting time, but once you have done your reservation, this waiting time becomes 15. So you have many questions about ensuring that you're serving all these passengers correctly and assigning them to the right operators. Also, you can only control the proposition that you're making, but finally it's the riders that will decide which proposition is picked. So you will need, for example, to have some discrete choice model on the rider and see perhaps based on the incentive that you can put how a rider will behave. And so to do that, you can control the incentive. So for sure, the first one is the price, but there is other incentive. For example, you can think about preferential parking lot, or simply you can reserve your parking lot in advance, so you know exactly where you will park. You won't be too far from the bus, and so on. So people can also react to those incentives. It's not just about price. And also from the privacy point, you want to control the information shared with the operators. So every time you have a request, do you want to share all the information with the operator that is doing a ride sharing, or you just want to offer partial information to protect a little the privacy of the user, and so on. And then you can also take into account fairness to ensure that everyone is served correctly by the system. And so, as I say, you have a very complex distributed optimization problem with partial information, so multiple agents, the riders, the operator, and the central platform, and everybody collaborate and interact together. But when you are trying to solve this optimization problem from the central platform, there is many things that you do not control. So here, I won't get into the detail, but that's the type of architecture we try to design, where you have all these agents and how they communicate, share information together, wait for feedback, and see how you can convert to right assignments between operators. And
question.
Yeah.
So, are you at the end solving some deterministic problems, or is it more stochastic?
For the moment, it's deterministic, but it's dynamic. So we don't take too much into account the uncertainty, but you resolve the problem every minute or things like that.
Because if the system is distributed in some way, then probably the prediction aspect would be much reduced, because if I have a lot of data in the present form, I can make good predictions. But now the moment the data is not available in particular form, it will affect my predictions, and then in turn the optimization.
Yeah, for sure. If you want, if you can have perfect information, that would be great. But the reality, and as I said, for example, with the new laws that you have, is you won't have the right to get all this information to have a good prediction. So you don't have the right anyway to use that data. So that's why you have to find mechanism to be able to get valuable data for your optimization problem, but still that respect the law and respect the privacy of the user at the end. So let's go to the last part of the talk about now that you are, as we've seen, for example, here on this picture, something that you may like also to have is synchronization of the system. So for example, when you have your shuttle that arrive here, you have a bus that will leave in 1 or 2 minutes. You don't want to arrive there with a shuttle and then wait for 20 minutes for the next bus. So how do you do this synchronization? So you really need that when you have a multi-leg trip. So it means that you have different legs in your trip. So for example, a shuttle and bus, or your carpool and bus, and so on. And what you really want for passenger is real-time synchronization. So for example, if you have some delay because the travel time, your trip take a little more than one was expected, and you arrive 1 minute late, ideally you may want that the bus is waiting for you for 1 minute before leaving, especially if the bus is just going there every 20 or 30 minutes. But how can you ensure the synchronization? So if you're in the same, if it's the same operator, it's easier because you have just one person involved and you can decide to solve some optimization problem and you don't have some collaboration to manage. But across operator, that's another story, because you need to find also common ground and accept some techniques to be able to have some collaboration between the operators. So if you look at a centralized system, so let's say that there is a big system that control everything. I won't say it's easy, but the main issue is scale. So it's just you start to have very, very large systems, and in terms of optimization, it starts to be very difficult to solve. But if you have a distributed system, it's a new universe of challenges, because it's not just a question of scale, it's a question of collaborations between your agents and rules that you need to set for those collaborations. And that will have a huge impact in terms of optimization. So let's look, for example, to a problem that we are currently solving here just for the STL, so one operators. So how can you ensure that you have synchronization between two buses that belong to the same system? So you have the first bus here that are going from point A to point B. Then you have the second one that brought you to your final destination. And so you have a point of synchronization here where you may have to wait. So especially if the second bus line, for example, is a low frequency one. So for example, the bus is going there every 30 minutes. You want to ensure that you don't drop the passenger just 1 minute after the bus just left. So the passenger will have 29 minutes to wait for the next one. So there is different techniques that you can implement to try to do that. So for example, here that the most common, so hold. So it means that you just ask to the bus to hold at the current stop to wait for the bus, the other bus to arrive. You can have also skip stop. So it means that the first bus will skip some stop to arrive faster to this transfer point to ensure that we will be able to make the transfer. Or you can also ask the bus to speed up a little to be in advance on the schedule, or perhaps if it was late, to be on schedule to be able to do the synchronization. And it's pretty tough as a problem, because the main issue here is you don't know if someone intends to transfer. So you have people inside the bus. You can try to predict the person will take the next bus as a transfer, but you don't know for certain. So how can you implement those tactics without having, I would say, the full pictures of what will happen? And so what we do currently is we have a hard flow model to model all those techniques, and we use online stochastic optimization to try to, based on prediction, choose the best tactics or combination of tactics to, I would say, increase the number of successful transfers that you can have. So that's the kind of hard flow model that we have. Thanks, Laura. So here, each line here corresponds to a bus trips. So let's say this one is the first one of the, so the leg 2, that's the first bus, let's say leaving at 10 a.m. And here you have the second bus that will leave at 10:20. So here the passenger, so that's the, for example, the normal bus line or schedule. And if you decide to wait a little here, you can delay a little, but perhaps you will be able to pick up the passenger that otherwise will have missed the bus and took the next one. And so what we try to do here is to minimize the average trip time of all the passengers. So if, in terms of results, what we get here is here you have 5 blocks. So the morning rushers, evening rushers, and early morning, midday, end of services. And it's the averages on many buses from the data of the STL, so at Laval. You have 3 bars. The first bar corresponds to what really happened with the STL. The second one corresponds to what we do when we implement the tactics with the online stochastic optimization. And the last one corresponds to what will happen if you add perfect information. And so here I would say the main thing is there's 2 things. So here it's the total, perhaps average travel time for passenger, and each color corresponds to the share of each part to the travel time. So for example, if you take the green one, it's the travel time inside the bus. If you take the yellow one, is the wait time that you have at bus stops. Normally just the bus waiting. And the one I would say that is the most interesting for here is the wait time that you have at the transfer. So from when you arrive from bus 1 and you have to wait for bus 2 on the picture that we have, that's the average time that you have. So it's pretty high, as you can see. And the idea is by doing some optimization, you are able to reduce that part. And it's exactly what you can see. Here it's much smaller in most of the cases. And we have been able to reduce a little, in general, the average waiting time. But as you can see, for example, on this one, during rush hour, where because the lines are, you have more line and the frequency is higher, you have less issue. And as a result, when you start to implement some techniques, you can see that the average increase a little. As you don't have perfect information, sometimes you will ask the bus to hold for nothing. You will ask the bus to skip some stop for nothing, and so on. So you don't know if the tactics that you implement will always be useful. So if you look in terms of bus travel time, so here in green is the bus travel time, and here it's the bus dwell time, so it means the bus at the stop. And the very small line that you see here, it's the hold time. So you can see that what we ask to the bus is very small compared to the rest. And if you look here in terms of number of stops where we had some tactics implemented, you can see that the maximum is between 6 and 7% of the stops. Finally, we look also at the passenger travel time variation between what currently you have at the STL and what will happen if we were able to implement those tactics. And you can see that in average, you remain the same. You have one passenger here that has an important increase on the travel time, but most of them are pretty good. And the huge difference is all those ones where you can see you can have a big decrease. It's all the passengers that would have missed the connection without any tactics. And you can see here it's the same, it's mostly those one and that are pretty reduced. So the next question that we have, and that starts to be more difficult and it's more open work, is how can ensure synchronization across operators. So type of techniques you can think about is, for example, you can lock a bike in advance. For example, if you want to have a big C ready for you, so when you alight the bus, you don't want to find an empty rack of a big C. So if you book the travel through the platform, we can perhaps lock a bike for you in advance. Same if you are using Communauto, we can think if there is a Communauto, I don't know, at Cartier, at Laval on the parking lot, you may like that we book the car in advance for you. Same, you can reserve parking spot for you in advance. And also we can ensure the on-demand shuttle is waiting for the passengers. But it's exactly like the same that we have seen, is even if people book and so on, you won't be able normally to accommodate everyone. If you lock a bike, you want to be sure that the bike will be used. It means also some other passenger won't be able to use the bike. Perhaps you will have also to predict, perhaps you can release the bike because you have predict that another bike will arrive between, and so on. So there is many questions about efficiency on how you can manage all this synchronization and implement service that you can offer. And then you can add another layer is in terms of synchronization, you can think about new services. Perhaps you can do some parcel deliveries. So if you are alighting from the subway at Cartier, and you are taking, imagine, a Parco bus in Laval, and you are taking an on-demand shuttle. Perhaps if you were waiting for a parcel, the parcel could be inside the shuttle already and waiting for you, and you just have to take the parcel with you when you arrive at your home. Or you can think there will be some lockers, you take your parcel in the lockers, and you go on and so on. But the same, you need synchronization between services to ensure that you will go to this hub and that the parcel will be waiting for you. And you can think the same about food delivery or plenty of other services that could be plugged into those mobility systems. So the big take-home message of this presentation is there are many transversal issues that arise in this integrated mobility system. So about legal, ethics, governance, privacy, distributed system, and so on. And if you want to take them into account in the way you design your optimization problem, there are many challenges and many issues. And as we've seen just for the two last one, assigning passengers to operator or synchronizing services already raised many issues about that, and mainly it comes always to the data that is available and you can use, and ensuring that you are fair and you are still serving everyone. So thank you for your attention.